Okay, so I'm going to try to go over the key ideas in Chapter 2 real quick, just to kind of get us a head start. I mean, hopefully you read that, hopefully you are doing the homework, but sometimes it helps to see some of the big ideas that written down, and that's what I'm going to do. Okay, so it's not going to cover everything, it's just the bigger ideas. And I'm going to go fast, because you could pause it. Okay, so the first is vector addition. I already talked about this before, but if I have vector A plus vector B, how do you do that? Well, graphically isn't as useful as the real way. What I can do is I can write A like this is AX x hat plus AY y hat, and I'll assume there's no Z component for now, and B equals BX x hat plus BY y hat. Then A plus B equals AX plus BX x hat plus AY plus BY y hat. Now, how do you find these? You know, you have to draw a it helps to draw a picture to find the x and y components. And the AX component could be positive or negative. So if that's negative, then make sure you put it in there. Okay. They could both be negative. Then you're adding two negatives, which makes something more negative. If I want to do A, oh man, marker's dying. Right in the middle. Okay, I'm switching to red. I could do A minus B, and that would just put a minus there. That's it. Okay, that's vectors. So what about I think the most important idea in this chapter is the following equation. F net equals 0. Okay, this is, that's a Newton's first law. I mean, come on, law, small, it doesn't really matter. Okay, it is what it is. Experimentally, if we look at all the forces acting on an object, and if they all add, if it's in equilibrium, this is true in equilibrium, then all the forces have to add up to the 0 vector. Okay, now it's important that you draw this correctly. This side of the equation is a vector. The total force is added up as vectors. Then that side has to be a vector too. Okay, what is the 0 vector? 0 vector equals 0 x hat plus 0 y hat. And you say, well, that's just 0. No, it's not 0. It's still a vector. Okay, that means that this is 0 in the x direction and in the y direction. Okay, so I actually write this as f net x equals 0, f net y equals 0. Okay, those are two scalar equations. That's a vector equation. 0 vector is a thing. Okay. Free body diagrams. Free body diagrams aren't the truth. They're just a very useful tool. I mean, vectors are just a useful tool also. Let's say that I have, let's just say I have two objects and they're hanging by a string like that. Okay. The free body diagram says, let's try to represent all the forces on one object. In case, let me choose this one, and draw those forces as vectors. So if I want to draw the forces on this, I can break that into two types. There are forces that are due to contact interactions, and there are forces due to long-range interactions. Now, at this point, there's only one long-range interaction that we're going to see, and that's gravity. Everything else is a force because something's touching that. Okay, so what's touching this? Well, this rope is touching and that rope's touching. So I'm going to say T1, T2, and then I'm going to say gravity. So that'd be mg. Okay, so that's a free body diagram right there. Some things to think about. It doesn't matter, at this point, it doesn't matter where it touches that object. I just redrew the object as a point. But it does matter, and it doesn't matter actually where you draw these forces. I like to add them, so that one I didn't even put on there. I added it to the end of that one. Okay. But that way I can easily visualize what forces are acting on that object. It's all the forces acting on that object. I didn't draw the gravity on this one, on that one. Because gravity, the gravitational force, is pulling on that object, not at that object, and I'm only drawing the three-body diagram for that object. Okay, moving along, because we got to go fast. Gravity. Let's talk about gravity since we're doing that. If I have a planet and an object right here, any two objects with mass have a gravitational force between them. I can calculate the magnitude of that. If this is a distance r between their centers, then the gravitational force is g m1 m2, this is m1, this is m2, over r squared. Now that's not a vector. The gravitational force vector, if I'm looking at this one, it pulls it towards it, so it would be that way, F. And this one would be that one. But here's the cool thing. This is the same interaction. The two are pulling each other together. So the magnitude of this is exactly the same as the magnitude of that. Mass 2 pulls on mass 1 with the exact same force, magnitude-wise, that 1 pulls on 2. They are the same force, just two different parts. Okay, but G here is a constant, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Now, if I'm close to the surface of the Earth, then I can approximate this gravitational force as F equals mg, where g is the gravitational field, and near the surface of the Earth it has a value of negative 9.8 newtons per kilogram y hat. So it's down and has that value. That's an 8. Okay. It's better to say 9.8 newtons per kilogram, not meters per second squared, although they are equivalent. Normal force and friction. Okay. Yes, I am flying through this. Because if you didn't read the book and you're just relying on this, it's not going to be a good day. You can read the book too. Let's say I have, let's just look at this. Here's a book on a wall like this. In your book. Here's a block. And I can push straight that way, and I can hold it up. Hopefully you can see that. So in that case, I'm pushing this way. F finger. Well, it's at equilibrium because it's not changing its motion. So what other forces are on it? Well, I have gravity. Okay, those can't be it because they're in different directions. So I have two other important forces. The wall exerts two forces. One is an upward force. It's parallel to the surface. We call that friction. And the other is perpendicular to the surface. We call that the normal force. And those are the two things we want to talk about. So normal force is a force perpendicular to the surface that pushes things away. Okay? You can't determine the magnitude of that without knowing other things. Because the harder I push this way, the more the wall pushes back. Now what about friction? We have two models for friction. We have this model. We'll call it static. Actually, this is just the magnitude. The magnitude of the static friction force is some coefficient that depends on the two types of surfaces, wood and board. Okay, that's a unitless coefficient, and the magnitude of how hard they're being pushed together. And this is just a model, okay, but it works really well. But this is going to be parallel to the surface. Well, I didn't put a vector here because I had to put a vector there, and they're not in the same direction. They're not equal. Okay. The less than or equal to means that the friction, static friction, does whatever it needs to do to prevent it sliding up to this value. Okay. Now, if it does slide, then we have this. Fs kinetic is equal to mu k n. So now we have a different value for the kinetic friction, but still, and it doesn't change no matter how fast the two things are sliding. Okay, the last thing, tension. Say I have a ball with two strings on it like that. the tension in the string is like the normal force in that it pulls however much it needs to keep it stationary. But there are two important points. Strings can't push. So I can't, it's going to have to be pulling that way. T1, T2, they pull. Strings pull, they don't push. Two, they only pull in the line of the string. You can't, it couldn't be a string like that with a tension like that. Okay, so the direction of the string is the direction of the force. Okay, that's it. I know it was fast, but at least it gets you started.